In this lesson, we will explore how triple integration is used to calculate the volume of a three-dimensional solid. We represent the solid region as E in a Cartesian coordinate system. The volume of a solid is found by integrating the constant function 1 over the region E. The differential element dV represents a tiny piece of volume, defined as the product of dx, dy, and dz. To understand the process, imagine the solid is composed of many tiny rectangular boxes. Each box has dimensions dx, dy, and dz, and the triple integral sums these boxes together to fill the entire space. To evaluate the integral, we first determine the boundaries. We project the solid onto the xy plane to find the region D, which helps us establish the limits for our first integration step. The inner integral typically covers the z-axis. We define the height of the solid by its lower surface, u1, and its upper surface, u2, both of which are functions of x and y. Once the z integration is set, we look at the 2D projection D. Here, we determine how y varies as a function of x, and finally, the constant numerical limits for x. This results in an iterated integral. We solve from the inside out, first with respect to z, then y, and finally x, following the boundaries we established. Integrating 1 with respect to z gives us z, evaluated from 0 to 1, which is 1. Repeating this for y and x consistently yields a total volume of 1 cubic unit. Beyond just volume, triple integrals allow us to calculate the mass of an object if its density is known. By replacing the constant 1 with a density function, we find total mass. In summary, triple integration sums up differential volume elements across 3 dimensions. By defining boundaries carefully, we can find the volume of any 3D solid. Generated by Vision Solve AI.